Hello and welcome. My name is Romano, and I am here with our team leader, Stetina, Bryan, Stebbins, and Yifan, Zhang. And we are senior project team number 16, Assistive Technologies. And for our project, we were to design and construct a wheelchair attendant brake. Our faculty advisor is Dan Mazzucco. Our industry advisor is Susan Foster of Elwyn, and our senior project coordinator is Professor Victor Marcus. So real quick, what is Elwyn? Elwyn is a nonprofit organization that takes in people with both mental and physical disabilities in hopes for them to re-enter the workforce. So because they're nonprofit, they depend on both donations and the insurance companies of the patients that they have there to gain these wheelchairs, causing them to have several different types of wheelchairs at the facility. So the problem that they came to us with is that because of these disabilities, the patients in the chairs tend to disengage the normal handbrakes that you see on normal wheelchairs, not knowing the harm that it can cause them, whether they're on a ramp or on a wheelchair lift or something like that. So that's why our braking device had 5 requirements. First, most importantly, it had to keep the chair stopped. Secondly, since they have so many different types of wheelchairs, it had to be both detachable and adjustable. Next, it had to be attendant activated, meaning that only the pusher can activate it and deactivate it. And going into our last point, it has to be easily engaged and disengaged by this attendant. So now I'll turn it over to Bryan to talk about our schedule.
So here's an quick overview of our schedule. And we had an interesting situation in the beginning of the year. We were given multiple projects to choose from, not just one specific project. So as you can see, we ended up going with the wheelchair handbrake. And the reason we ended up going with that one is a few reasons. First, it's mechanical in nature. And secondly, we thought as a team it would provide us with good real-world experience that provided us with a unique challenge. And once we knew what our project was, we instantly made a prototype in SolidWorks. Once we had that going, we improved on that with our final design you see here. And in the last 2 months, we have procured our parts, we have fabricated our design, and we are almost 100% done with our testing and evaluation. And I'm going to hand it over to Eric, who will talk about everything.
Here is a picture of our completed overall design. I'd like to point out the 3 main features. Down at the bottom, you have the braking feet. You have the linkage system, which attaches at the axle, and then you have the activation bar in the center. I'll now go into greater detail about these 3 features. Okay, the first feature is the braking feet. The braking feet are the 4 points of contact between the chair and the ground, and these are what actually keeps the chair from moving. There are 2 nut and bolt connections involved here. The first bolt connects the foot to the aluminum structural member. The second bolt contains roller bearings, and these roller bearings are important because they force the wheel to spin in place instead of translate along the ground. The last thing included in the braking feet are these limit bars. We installed these bars so that the feet will not over-rotate around the bolt upon deactivating the brake, and they also ensure that the feet rest properly on the ground when activating the brake. The next feature is the linkage system. As you can see here, there is a hook which attaches so that the linkage system attaches to the axle of the wheel. We did this so that we could accommodate all chairs with 24-inch diameter wheels. Also included in the linkage system are extension pieces down at the bottom. This gives us 1 to 2 inches of adjustment so that we can account for different tire thicknesses. The last feature is the activation bar. The activation bar was made out of PVC piping. It completes the design and allows both sides of the braking mechanism to move together and simultaneously. The activation bar also accomplishes 2 of our original requirements. The first, that it is out of reach up from the passenger, and second, that it is easily activated and deactivated by the attendant because the attendant can use their foot to do this. At this point, we will now show a short demonstration of our design in action. At this point, the brake is disengaged, so the wheelchair is free to move. You then come to a stop and engage the brake with your foot. The wheelchair can no longer move, and the wheels will spin in place. At that point, you can disengage the brake, and the wheelchair can then move freely again. We'll now pass it over to Yifan to talk about the drawings behind our design.
Before we did these draft drawings, we made some measurements of the wheelchair. Then we did some calculations about geometries, like the length of the leg, and the size of the foot, the angles, and the space between wheel and ground. Then we verify our calculation by using SolidWorks and got this draft drawing. The big circle here represents the wheel, and the horizontal line is the ground. The solid line represents the engaged position. The foot engaged with wheel and ground to keep the wheel from moving. The dashed line represents the disengaged position. When disengaged, the leg lifts up and the foot swings away from ground and wheel, so the wheel can move freely. Based on these draft drawings, we finalized our dimensions and made these 3D models and animation. This design is much simpler than our initial design, which will be mentioned later. It contains only 5 different parts. They are the hook, the leg, extension piece, and the middle piece, and the foot. The hook is used to attach to the axle, and the extension piece has slots on it. So the overall length of the leg can be adjusted to fit different tire thickness. And the middle pieces helps the system lock in position. As you can see here, when the leg is lifted up, these middle pieces are not aligned. They angled a little bit and contact with the bottom of the hook. So the leg is not falling back again. Now I'm going to pass it to Eric.
In order to fabricate our design, we first needed to purchase standard sizes of aluminum, sheet metal, and PVC piping. We then worked with Rich Karkonig in the machine shop to cut these materials down to size and drill holes in them based off of the dimensions we came up with in the SolidWorks program. The last key component of our design was deciding on what material to place beneath the feet. We needed a material that would maximize friction on a variety of surfaces, whether it be tile, carpet, or cement. We also needed a material that would not wear over time and that would not damage the ground. We chose to test a material known as Silguard 527. We did this because we could control its property of coefficient of friction. We needed to determine the best ratio of the 2 silicone gels that come in Silguard 527. That testing is still in progress, so as a prototype solution, we decided to just put sandpaper beneath the feet of the braking mechanism. We do realize that this is not a long-term solution, however, because that sandpaper will wear over time. I'll now pass it back over to Bryan to talk about the budget.
So we were allotted $350 by the School of Engineering. Of that, we spent roughly $74 on structural members. This includes the steel that we made our hook and our feet out of, and includes the aluminum that we made our linkage system out of. We spent another $64 roughly on nuts and bolts, which is our hardware and our roller bearings. And we spent another $85 on stopping material. That is the slide guard 527, the silicone gel, which we're doing testing on. And we allotted another $100 for the poster, which leaves us with roughly $27 under budget. And this is a quick schematic of our old design. A few limitations or challenges we have with our old design. Our first thought was to attach it to the underframe of the wheelchairs, but as Rich mentioned, they have multiple different types of wheelchairs there at Elwyn. So the varying diameters and heights of the frame underneath the wheelchairs vary a lot. But the one thing that remains constant is the diameter of the wheels, which are 24 inches. So what we are doing with our design is we're attaching it to the axle instead of the frame. Now that eliminates the problems with the heights and the varying diameters that we needed to do with our original design. And also original design had a height varying system for that. We don't need that anymore, or it's now simplified, which is one of the main things we want to do. We want to simplify our design. So, and then another thing that we wanted to improve on was, it was cable activated. Our original design went right up to the meter brake that you could activate, deactivate the design with, which made it simple in that sense. But it added another level of complexity to it in the actual manufacturing. So what we ended up doing is, how you can see here, we put a simple PVC pipe to connect our connections together, made it foot activated to simplify the design as a whole. And I'm going to throw it over to Rich to continue on.
Some of the enhancements that we can make to our design if we were to continue the development of it is first, definitely find the specific ratio of the sill guard to maximize the friction between the feet and the ground. We could also do some other material testing to still maximize the strength while also minimizing the cost of the different materials. And overall, what we did, we created a practical way to make one of these bricks, although it might not have been a practical way to make 100 of these. So in the future, we can find a more economically efficient way to find a way to mass produce these bricks at a cheaper cost. So in summary, we were given a problem, we created an initial solution, we then improved that solution, and then created a working prototype. As Bryan said, we came in under budget, we were on schedule, and it did fulfill the 5 requirements that we set forward to it. And as you were supposed to see in the demo, it was, in all other demos, it worked and kept the normal forces of a person sitting in the chair. But now we would just like to thank all those people that helped us throughout the year, especially Professor Nicosia, Rich in the machine shop, and Susan Foster over at Elvin. So again, we are senior project team number 16, Assistive Technologies, creating a wheelchair attendant brake. Now I'd like to throw it over to you guys for any questions.
We'll start here in the back.
And then your calculations took into account a horizontal surface. Real world application, the wheelchair would be encountering ramps. Were calculations done to address wheelchairs being pushed up ramps that your brake wouldn't interfere with that?
We did not do any actual calculations for this, but we did address that issue, and the limit bars allow for some rotation to so that the feet will still come to rest on an inclined surface. I believe our calculations were just on a horizontal surface.
And we test it on the run. It works perfectly. And because it's not using sandpaper, probably the sandpaper is wear out. That's why it's not
The
working.
concern is that you're pushing it up and all of a sudden your brake isn't stuck in the side of the ramp that you can't push the wheelchair up any further.
Right.
You used the sandpaper in a test. What grade of the sandpaper was used and what criteria you used to select the material for the test?
The sandpaper is for quick prototype, and it's just use super glue to glue beneath of the feet, and it has great friction. But it will harm the surface, and it can be wear out. And we use other material like rubber material. It can apply enough friction, and it not harm the surface, and it can be used many times.
It was just a standard material, a coarse sandpaper from Home Depot. The prototypes we picked up.
How do you consider the efficiency of the brake?
Excuse me, what was that?
How do you consider an efficiency of the brake?
Yeah, as a prototype, we considered it was efficient because it can withstand the typical force of someone in the chair.
You, sir?
Yeah, I have a nephew who's handicapped. He's in a wheelchair all the time. His strength in his arms from being in that wheelchair his whole life is strong. How do you measure against someone who has the ability to possibly move the chair with the brake on?
That was actually one of the problems that Elwin was having, because they say that with the normal brakes, they would just push right through them.
Right.
They said that the maximum weight of a person there would be like 250 pounds. And since the roller bearings, they would actually just cause, no matter how hard you push it, they'll just keep rolling in place because of the roller bearings.
And we can try it one more time. Hope this time it will work. You see?
I'll go in the back first.
because the attachment to the axle was a vertical swap, seems like that will loosen up over time. Why didn't you do it the other way around? So it would be held in place by the weight of the wheelchair.
I think that we,
Well, one of the things that we needed to do is make sure that it was detachable and be able to put on different wheelchairs. So we had to make it so once you take off like one of the feet, it can still slide out of the wheelchair and be put on another wheelchair. I don't know if that answers your question, but.
That's great.
I had a question, since obviously this design will be removed from your hands and put into a facility, the repairability and the durability of such a product that is going to be used by different people. I can see with the PVC piping somebody who's pretty big as an attendant just kind of pushing it down. How did you think about that kind of wear and durability of the product?
we know that at Elwyn, they have 2 service repair women who have plenty of spare parts to make replacements on any type of wheelchair pieces. So when we met with them, they were very experienced with making types of repairs. So we're confident that they would be able to deal with our braking mechanism as well.
Yes, sir, in the back.
When you were selecting your PVC material and sizing it, did you select Schedule 40 tubing, or did you use a lesser wall thickness?
I'm not sure about what exact thickness we used. I know that the inside diameter was 1/2 inch. That's the one we used, but I'm not sure about the actual wall thickness in that terms.
You, sir, in the blue.
This project seems very beneficial for several reasons. How do you feel about encouraging your next classes to pick up where you left off and try to improve on what you have?
I think it could definitely be continued, and the fact that there is an organization that actually needs this need in a real world situation gives great satisfaction if we would see it actually being used. So I would definitely encourage a future group to continue the project.
Yes, sir.
Did you check if your design is compliant with any ADA regulations? Can you just add on to our wheelchairs anything, or do you need to check compliance?
I don't believe we checked any of the regulations. Maybe.
But we did calculate the safety factor is at least 5, about 5.
For assistive technologies that are maybe applicable ADA regulations by the federal government that we can comply with before it is put out on the market.
Thank you.
So that brings us to the end of our